last class. I'm gonna get the test back and go through them. When you get your test back, probably more than the other tests I've returned, make sure you check my edition. There were a lot of part marks, mostly resulting from sig fig errors. In some cases, units missing, in some cases, incorrect formulas, but my point is there's a lot of fractions or a lot of halves. So I made several mistakes, not so much last block, but I made several mistakes in block E, probably because I was marking that during the football game last night. But there's a very real possibility that there could be addition errors. Obviously, if you think there's other things that need to be changed, once we're done going through the whole thing, by all means bring them up. For the most part, the test was pretty good. And as I said, I think last class, by now it should have made sense. Like you should have been able to wrap your head around, conversions, moles, multi-step problem solving, that type of thing. And that's going to be required really right up until the end of chapter 4. And we'll be proving that when we get to 4.5 and 4.6. So the test, part 2, it said it was out of 27, it's actually out of 28. So 28 and 16 adds to 44, but the 4 extra marks in part 2 meant that technically you could have gotten 32, which meant technically there was a possibility to get 48 out of 44. I don't think anyone got 48. Some people in the other classes, I think there were a couple 47s and a half. Even if you didn't do the bonus question completely correctly, if you got something for it, those are free marks. Okay? These are in no particular order. So the test is not out of 48, it's out of 44. Okay? Samantha Lowe.
So fast.
Allison. Ariana. Christina. Leah. Brienne. Lauren. Cassandra. The other Samantha.
There's 2.
Daniel Cartina. I wrote Be careful, because your ones look like sevens.
Oh, he probably draws it with like that little. Oh, let's do this. Yeah. Oh, shoot. Yo, I just folded one. What's that?
Alexandria.
It's too nice. Too
Julian. Ryan.
Oh,
Julia. Olivia.
yes. Oh, the next one's mine.
Annabelle.
Is that that's mine? It's mine, maybe. 42. Thank you.
Lucas.
Thank you.
Lucas.
I was right. 42 plus 13.
Erica.
Wait, what? That's 55 then. See, I knew I put that.
Nicole.
I got 4 months on the ring. Hell yeah.
Granville.
What was I doing here? 7 words. 4. 3.5.
And Claire. I assume this is yours,
2 6.
but you didn't put your name on.
Oh, it's supposed to be 2 6.
That's the only one left, so it must be yours.
2 6.
So let's start
Fair enough.
with multiple choice. So I just took pictures of those pages and emailed them to myself. I'll put them on the screen. I might have to turn part of the lights out because it doesn't seem to show up too well.
That's tragic.
I think I can make my computer a little brighter. Hang on.
What'd you get doing that? That's easy. Oh, shit. See, I can get the written. I just can't get this. This is always what brings me crazy. I can't get either. Yo, what if I'm a sleeper agent? Like, exam day, I just log in, like, yo, I absolutely died in the exam. I fucked up 3 questions. I would have gotten 45 if I didn't fuck up 3 questions. Hey, you know how close that is? That is really close. But you got 42. That's basically that's 95%. That's pretty good. It's really good.
You might not be able to read
Compared to my first test. Grant, what'd you get? 100? 42. I got 42. What'd you get? What'd you get? 44.
I'll read it for you.
She got 45.
So question 1 reads, Joseph Louis Gay-Lussac is credited with finding that gases combine in simple whole number volume ratios.
You know what's funny? It's the 3 questions I guess.
Combine in simple integral volume ratios suggests
actually
to
crazy.
Avogadro that meant that the volumes had something to do with the number of particles. And that led to question number 2. Which statement represents Avogadro's hypothesis about gases? At the same temperature and pressure, equal volumes of gases contain equal number of molecules. So that the whole numbers in the formulas were based on the whole number volume ratios. So volume has something to do with number of gas molecules. Number 3, the molar mass of lithium fluoride. It's a 1-to-1 ratio, so 1 mole of lithium's mass plus 1 mole of fluorine's mass, 25.9 kilograms. Number 4 reads how many moles of sodium hydroxide are present in 80 grams. To the nearest gram, the molar mass of sodium hydroxide is 40 grams. So that's 2 moles, which was C. Number 5. How many moles of water are contained in 36 milliliters? Well, the density of water is a gram per milliliter. So 36 milliliters is 36 grams. And to the nearest gram, that's 2 moles because water has a molar mass of 18 grams. Number 5. Which of the following masses contains the largest number of atoms? Well, you'll notice that 31 grams of phosphorus is a mole, 27 grams of aluminum is a mole, 23 grams of sodium is about a mole. So those different masses all contain the same number of atoms. But the smallest mass, 20 grams of helium, is actually 5 moles. So the smallest mass contains the greatest number of atoms because that element has the smallest molar mass of that quartet. Okay? And moles is a number. Assume you have 4 22.4 liter flasks, each containing a gas at STP, which means you have a mole of each of these gases. Which of the following flasks will have the greatest mass? Well, we've got neon, which is a noble gas, which never exists as a diatomic molecule. And then we've got 3 gases, all of which exist as diatomic molecules. So flask B contains N2, a mole of N2, which is 28 grams. Flask C contains O2, a mole of which is 32 grams. Flask D contains F2. Again, another diatomic mass, and the molar mass of fluorine times 2 is greater than the molar mass of oxygen or nitrogen times 2. So B. Now, neon has a greater molar mass as an atom than nitrogen, oxygen, or fluorine, except elemental gases that are diatomic do not exist as individual atoms. They exist as diatomic molecules. Okay, so you had to know a couple of things for that. The empirical formula for a compound containing carbon, hydrogen, oxygen, you can't see it from where you're sitting, but it's C2H4O. The molar mass of the compound is 132. So to the nearest gram, the empirical molar mass of C2H4O is 44 grams per mole. The actual molar mass is 132 grams per mole. Notice that units cancel, leaving you with the number. So that means even though that is the empirical formula, all of those have to be multiplied by 3, which gives you C6H12O3. In number 9, if you spent time doing any calculations, it was wasted. The question reads, which of the following solutions is the most concentrated? Concentration has nothing to do with volume. So if you multiply volume by concentration, you're getting moles. That's not what the question asks. Which of the following solutions is the most concentrated? And 1.2 is greater than 1.25 or 0.5. If you had 1 milliliter of 1.2 molar, it would still be more concentrated than any volume of the other solutions because they have a lower concentration. And if you multiplied volume times concentration, 2 of them gave you the same number of moles, which suggests maybe you weren't doing it right. But this is meant to be answered in 5 seconds. And if you spent time doing 4 multiplications, that's time, number 1, that was wasted. But it also meant you misread the question. So when students run out of time, these are some of the reasons. That is expected to be answered instantly if you know what concentration means. There's no math attached to it at all. If the question said which has the greatest number of moles, then you do multiply volume by concentration. But that's not what it asked. The next one you need that for. In 7.75 liters of a 12 molar solution, that should read 9.7. How many moles of the solute are present? Well, in every liter you have 12 moles. If you got 3/4 of a liter, you got 3/4 times 12, which is 9. And I picked 12 molar hydrochloric acid because that's how I buy the acid from a chemical supply company, 12 molar. A 2 mole sample of sodium chloride is dissolved in water to give 0.5 liters. What's the concentration? Well, 2 moles divided by 0.50 liters is 4 moles per 1 liter. 4.0 capital M. And capital M is not the same as moles. Capital M means moles per liter. Some of you forgot that. Some of you thought the abbreviation for moles is capital M, and it isn't. The mass standard for one atomic mass unit is based on the mass of the isotope carbon-12. Specifically, exactly 1/12 the mass of the carbon-12 atom is what we mean by 1 AMU, or 1U. What concentration results when 20 grams of sodium hydroxide is dissolved in enough water to make 2 liters? Well, you can't just do moles per liter because I didn't give you moles, I gave you grams. So 20 grams in 2 liters times the inverse of the molar mass. Grams cancels. Sodium has a molar mass of 40 grams per mole. So that's half a mole in 2 liters, which is 0.25 moles in 1 liter, which is C. You're asked to prepare 1 liter of a 0.5 molar solution of sodium chloride. Which of the following represents the correct sequence of calculations? Well, the only way you can prepare it is determine the mass of sodium chloride you need. This would be the same answer as if 3 liters of 0.5 molar sodium chloride was evaporated to dryness. What mass would remain? So you're going to go volume to moles to grams. The only one that ends with grams is B. And if you want to use the mole, the real model again, volume to moles. And that's what you would measure out in a graduated container and add water to the final volume. So that's B. You didn't have to do the arithmetic, you just had to look at what's your calculation sequence. And then the last page. How many moles of oxygen gas are present in 56 liters of the gas at STP? So you want to convert liters to moles, so it's not 22.4 moles per liter, it's 22.4 liters per mole. So 1 mole over 22.4 liters gives you 2.5, 2 sig figs. And then number 16, the percent composition by mass of carbon in calcium carbonate is approximately. Well, the molar mass of calcium carbonate is 100.1 grams. 1 mole of carbon is in that 100 grams. 1 mole of carbon is 12 grams. So that's about 12%. Okay? You can almost do that one in your head. I would be surprised if you couldn't. So that's multiple choice. I don't need that anymore for part 2, at least not yet. So I'm not going to do all the questions in detail for you. I'll just go through what I expected to see on your
That's right.
So as I said I would do, number 1 was just like the last page of your worksheet. Yeah. Pardon me?
May I use the washing machine?
Yes. So remember the, how rigorous I was when I looked at that worksheet. I wanted to see units cancel. I wanted to see the right number of sig figs. So this had to be meticulous. Most of the mistakes with question number 1 were sig figs. Silver thiocyanate is this. Both of those ions are on your table. They both have the same magnitude of charge. 1 plus 1 minus, no brackets. 1 thiocyanate for every 1 silver. Obviously, if you didn't get the right formula, you also didn't get the correct molar mass. If you didn't get the correct formula, then obviously you can't get full marks for the remainder of it. All of your mass values on your periodic table you were given are to 2 decimal places. So when you calculate the molar mass, they all have to be to 2 decimal places. Okay? You don't round to the fewest number of sig figs when you add, you round to the same number of decimal places, or the fewest decimal places. But they're all 2 decimal places. So in 1 mole of silver thiocyanate, 1 mole of silver, times so many grams per mole, 1 mole of sulfur, 1 mole of carbon, 1 mole of nitrogen, it adds to 165.96 grams. Don't round it to 166. Round it, just leave it as 0.96, 2 moles. Notice that although the molar mass is to 5 sig figs, the number of moles that you're going to turn into grams is to 3 sig figs. So 2.50 moles times 165.96 grams per mole has to be rounded to 3 sig figs. So that's 415 grams. The next compound, that's chromium-3 permanganate. Without the 3, it's incorrect. How do you know chromium is multivalent? Because it's in your table as a 2 and a 3 plus ion. So chromium-3 permanganate. If you do the same rigor with the calculating molar mass in 1 mole of, you get 408.82 grams per mole. And some of you wrote really small, that's fine, but I still wanted to see the units and the canceling and the sig figs. When I gave you your test, as I always do, I said you can write all over the multiple choice section if you want. I'm just not marking it. So if you showed your work for that question on the multiple choice booklet, unfortunately, you're out of luck. Okay? If you want to show your work, do it down here as it was suggested, or do it here. But don't do it on the multiple choice paper, because I do not mark that stuff. Nor am I going to fish through the recycling bin and find yours among 85 others. I won't do that. Okay? Notice that there are 5 sig figs in the molar mass, 408.82. There's 5 sig figs in the mass you want to turn into moles. So You have to round, you have to leave that as 5 sig figs. 4.9985 moles. 5 significant digits. Now, although each sig fig error counts for a half, if you keep making them, that adds to something that isn't insignificant, pardon the pun. So if you see SD, that's where you lost me, okay? Number 2, one of the components of Kevlar used in bulletproof vests is called p-terephthalic acid. When this compound is analyzed, it's found to contain 57.83% carbon, 3.614% hydrogen, and 38.55% oxygen by mass. Determine the empirical formula for p-terephthalic acid. You had to begin with in 100 grams. The units had to go all the way through. Remember the steps. The mass amounts of each element are given or determined. You're doing step 1 when you say in 100 grams. 57.83 grams of carbon, 3.614 grams hydrogen, 38.55 grams oxygen. That's step 1. Then you have to convert it to moles. 4.8152 moles carbon, 3.5782 moles hydrogen, 2.4094 moles oxygen. That's step 2. Then you have to convert the mole amounts into the smallest integral ratio of moles. You're dividing all of them by 2.4094. Not 2.4094 moles, 2.4094. When you do that, you get 2.00 moles carbon, really close to 1.50 moles hydrogen, and 1 mole oxygen, which means the formula that you get directly from that last step is this.
So close yet so far. I know.
Okay? You can't leave it as 1.5. You do not round 1.49 to 1 or to 2. Your sig figs don't allow you to do that. So you have to multiply everything by 2. You get that empirical formula. Okay? That was worth 5 marks. The actual molar mass of the compound is 166 grams per mole. So you have to determine the empirical molar mass of that, which, as it turns out, is 83 grams per mole to 1 decimal place. Divide that into the actual molar mass, you get a multiplier of 2, which means the molecular formula is C8H6O4. I had to be able to follow your calculations, and you had to include units. If you care, this is what p-terephthalic acid looks like.
You just have to find the molar mass of this.
Somewhere in there, there's 3 double bonds. We often just put a circle around it to represent that.
It's just finding molar mass of the whole carbon.
And it's got
What am I doing?
an acid. Put either in. The P stands for para. Instead of those double bonds, usually you'll see this. This hydrogen is there, and hydrogen is there, and there, and there. P stands for pair, which is 1, 2, 3, 4. And then we connect this to another compound and we alternate. The compound we connect it to is called 1,4-diaminohexane or 1,4-hexane-diamine.
Speak English.
And it turns out to be a really dense molecule, and if you layer it, you get a pretty efficient bulletproof vest, although it's not the only one we use, but it's one of them. So, 5 and 2 goes to 7. The next I thought was a pretty easy 3 marks. One of the gases used in the trenches in World War I was phosgene, Cl2O. What volume were 435 grams of phosgene gas occupied when measured at STP? Well, you gotta convert grams to moles. Notice that you're given 3 sig figs in the mass. STP means 22.4 liters per mole, which is another set of 3 sig figs. although the mass you calculate is to 4. So 435 grams of phosgene times 1 mole over 86.90 grams times 22.4 liters per mole, rounded to 3 sig figs, should be 112. 3 marks. Number 4, describe how you would prepare 2.5 liters of a 0.50 molar aqueous solution, notice 2 sig figs, of sodium chromate, starting with the pure solid. Well, you've got to go volume to moles to grams, and when you get that answer, you have to round it to 2 sig figs. So 2.5 liters of solution times 0.50 moles of sodium chromate, which is this. It's not sodium dichromate, it's sodium chromate. Obviously, a different formula is going to get you a different mass, times a molar mass, which is 161.98 grams per mole. That gives you arithmetically 202.48, but you got to round that to 2 sig figs. And then the recipe reads, place 2.0 times 10 to the 2 grams of sodium chromate in a graduated container. Add water up to a final volume of 2.5 liters of solution. Don't add 2.5 liters of water. Or don't start with 2.5 liters of water and add the sodium chromate. You're going to get more than 2.5 liters of solution. And if your recipe was a little ambiguous, you probably lost a half mark. If it was wrong, you didn't get any. But add water up to, okay? And that's different than saying add up to 2.5 liters of water. Some of you said that. That's not the same. Adding up to 2.5 liters of water means you're going to add 2.5 liters of water. Add water up to a final volume of 2.5 liters of solution. Okay? And then the last non-bonus question, number 5. What concentration results when 41.75 grams of ammonium chlorate are dissolved in enough water to make 500 milliliters of solution? I thought this was an easy 4 marks. You can do it in one step.
So close.
But people ended up making it way harder.
Not close at all. So close.
Concentration is moles per liter. You're given grams per liter. So it's one step. So 41.75 grams of ammonium chlorate in half a liter. All you have to do is convert moles per liter, which means grams goes here. And 1 mole of the compound, how many grams do you have? 101.50 grams. Grams cancels. You want your final answer to 3 sig figs because of that. And when you do that, you get 0.823 mole, 4 moles per liter. Okay? For some reason, this posed way more of a problem than it should. All right? And then the bonus question. Because it was bonus, I marked it pretty rigorously. Okay? The one subscript in M1V1 equals M2V2, the one subscript refers to the solution you start with, the concentrated solution. The 2 subscript refers to the diluted solution. So you're not calculating V2, you're calculating V1. Okay? And remember the diagrams I put on the board. So, write M1V1 equals M2V2, and then manipulate it to solve for the unknown. So if we look at the question, describe how you would prepare 4 liters of 0.25 molar solution of nitric acid given a 16 molar stock solution. Now, you didn't need to know the formula for nitric acid. It doesn't matter because you're not calculating molar mass. You're not starting with the pure sodium. Okay? You could use the correct formula if you want to, but it doesn't make any difference. So we know the initial molarity, it's 16. We know the final molarity, it's 0.25. And we know the final volume, it's 4 liters. The only thing we don't know is V1. So V1 equals M2 V2 over M1. This is moles before the dilution, that's moles of solute after the dilution. They have to stay the same. This is always gonna be less than this, because this is always more than that. Once you have it in that form, put the numbers with units in it. The final molarity you want is 0.25 moles. The final volume you want is 4 liters. The initial molarity is 16 moles. Now, there's 2 sig figs there and there's 3 there, so we're gonna round to 2. So you can almost do this in your head. But when you cancel the units, you get 0.0625 liters. Rounded to 2 sig figs, it's 0.063 liters or 63 milliliters. So that's worth 3. Now the recipe reads, add 63 milliliters of concentrated acid to 3.5 liters, for example, of water. You're not gonna end up with 4 liters if you add 63 milliliters to 3.5 liters. You don't add water to the acid, ever. If you add any water to concentrated nitric acid, you're gonna end up wearing it because all of the water will vaporize. So you start with a little acid and a lot of water. And then your final step is to complete the dilution by adding water up to a final volume of 4 liters. That was worth 1, the calculation was worth 3. If you solved for V2, you probably lost something, because you're not solving for V2, you know it. If you had the wrong number of sig figs, you probably lost something. If you didn't put any units in, all of those things would factor into the mark you get. But even if you didn't get it completely right, those are free marks. And a number of people sort of depended on those free marks to give them a better grade. You got absolutely nothing to lose if you try it. Even if almost everything you write is rubbish, if you get something for it. Let's say you wrote M1 V1 equals M2 V2. You might get a half for that. But if you just leave it blank, then you're walking away from free marks. All right? The only reason I put it on there, not that it's hard, is because technically it isn't really part of the chapter we're in. Okay? Or the chapter you will be tested in. So, as I said at the beginning of the class, please check my edition rigorously. Sometimes I get a little bug-eyed after marking my 84th or 85th test, particularly when they're all different. Or if something else is better on television than me sitting around on my table and marking tests, sometimes I make addition errors. So, before you return your test, confirm that the mark you got is what you should get. And if it's not,
Can I get a half mark for
it makes the case when you come up and I'll change it.
Could I get a half mark for that, even though I forgot my units? Or no? Because it's all right. I just
Half mark for what?
for forgetting the units. Or no?
Well, I gave you 2.
Could I get 2.5?
No.
Oh, okay.
If you'd have not done that,
Oh.
I might have given you 2.5, but that just convinced me that all of this is a waste of time.
Oh, okay.
Yeah, so if, what you did is you multiplied volume times molarity with, again, no units, just saying.
Fair.
That already gives you moles.
Mm-hmm.
And then you did it again to get moles and grams. And the formula for nitric acid's wrong anyway.
Oh, is it?
So I think 2 is a really
Okay, that's
fair.
fair. That's fair.
Yeah. You guys, whether I made a mistake or not, I need part 2.
Okay.
So So if you need your calculator to add up the marks, by all means, and if I made a mistake, tell me, okay?
That's fair. I can't even
Oh, did we keep the multiple choice?
We can if we want to. I don't know. I didn't give it to my sister. That's so fair.
All of the markings on my test have been.
I didn't know what I was doing. I'm glad you gave me the tea.
This is so.
Yeah, I got nothing. 'Cause I literally started off wrong, and he just like, no.
Let's say it's 12. It's not 12.0. 12.01. That's when you take.
Just the 3 questions I guess,
Again,
bro.
that
The
looks
3
like
questions I guess.
14.0.
That's
Hey,
so
you're up.
14.01. But I looked at that one.
Wait, can I
All
check?
of these
Well,
are.
that's fair, honestly. I can't even lie.
So be
Yeah.
real careful.
It's been like that for me with every test. It's just fair. Like, what am I supposed to do?
I genuinely didn't know what I was doing when I did that.
So make sure that there's no mistake, because if I can't tell, I can't write. Okay?
So if I didn't do the extra step of calculating for grams, I would have gotten 3
Yeah,
or
except
2.5.
that's
We cannot be serious. Is it posted?
How do I check this? I've never used Periscope. Greatest.
Grades and attendance.
So I can't give you a correct mark for
Where's
that.
chemistry?
So
Just
that's
click it.
the wrong number and 6 grades. That's where the wrong
Hey, you know what? It's better than the C- on the first test.
Hey, he's getting up there. He's getting up there.
Yeah. So I did really bad on tests, but I get
C minus, C, C plus. Your next
Yeah.
grade, a B.
3 times 2 is not
calling it.
So yeah, I mean, that's why I said be careful.
Maybe I should try better.
That's okay.
I'm pretty happy.
Surely it goes up, right? Surely.
Hey, don't call me sure.
You want me to withdraw?
Have you seen that movie Airplane?
It's tough to
It's so bad. It's a terrible movie.
I'm at a 91 GPA. I'm at an 85. Oh my god.
More to go.
I only need 10 more %.
You can get that with like.
I don't care
what
about
else
the
would-
multiple
what-
choice,
what-
you guys. You can keep that if you want.
Holy shit. You know what sucks though? I could have been an 86 if I didn't. That hurts. That actually hurts.
Wait, well, what are the grades like? Can you think you can get 10% on? Or is it just this one?
It's just this one. My English grade I already know is gonna be
Are
10.
you Korean?
What? No, that's Chinese.
What's Chinese?
Luxong is Hong Kong. So I know that's always gonna be bad. There's no chance he's fixing it. Trent literally grades you based on how much you like it. And if you're a woman, it grades you how much you like it. I'm not even
For
joking.
finding that.
1%.
Like,
I'm 1% off.
genuinely, I just find this. I find this hard to believe. That just doesn't make sense to me.
I know, right? And then he marks this one out of 12. Like, I read that ass. I suck at writing anyway. So I can't even do that.
How much more?
As long as it's not a C+. Look at the rest of my grades.
It has
They're
to be a whole lot
semi-decent.
than this. So add
Besides
that.
those 80s, the rest of them are okay.
I think I was a C minus. So I think actually I went up. Despite my score, I actually went up, which is kind of crazy. Weeze is up.
We're coming back.
We up like a percent. No, I'm up 2%.
2% is better than no percent.
2% is less is better than getting subtracted. Yo,
Hey, we take that. We take
I
that.
gotta walk, bro. I mean, I don't really
The
need this.
trend is going up. So
Yes.
therefore, this becomes a bull market because we are
Yes.
investing to
Yes.
go up.
Yes.
We're expecting the market to increase. Why the I'm on something, bro. I had an energy shift before this. I'm so geeked.
It's not 3.164, it's 3.64.
Oh, I forgot to ask him how to round. I forgot to ask him how to round that question.
Yeah, he just took it. Like, what are you supposed to do?
Do that wrong. That's the wrong.
Simon, what'd you get? What'd you get?
My point is that when you
Yeah.
do this, it doesn't make sense.
91. Okay, that's not that bad actually. Pretty good.
I was like, I thought the test was out of 40. How do you get 91?
It's like 91. I was like, yeah.
Percent. I'm like, oh, okay.
44 times 0.91. Oh, we got 40.
If
Okay,
that's
that's
what you think you get, and therefore you get that, then this rounded to 1 is okay. So that so it's 2 mistakes. Yeah, that's what it is.
35 minutes.
You can round it to 1. Okay?
I have a question. What's your time?
Say louder, say louder.
I'll just look.
So let's split the difference. So that's 10 extra minutes. Okay, so let's go 39. Okay?
Really losing my.
Yes, what?
The question was like the 2.5 liters of 0.5 molarity. How am I supposed to round that to 3 sig figs?
That's 2 sig figs, that's 2 sig figs.
Or sorry, 2 sig figs. How am I supposed to round this to 2 sig figs? Because I rounded it to 1. Because I rounded it to 200.
2.0 times 10 to the 2 grams.
Oh, is
Isn't
that?
that 2 sig figs? Scientific notation.
Should be right.
Correct.
2.0.
Yeah, I never thought we'd.
The 2.
I never thought we'd be bringing that back.
Damn. All right.
Yeah.
That's fair.
Most of my learning comes after the test.
It's true.
Like I learn more
When
after.
we get to section 4 or 5, Sherry is going to begin that section by saying, do you remember how to write chemical formulas? Do you remember how to balance equations? Do you remember how to calculate molar mass? Do you remember how to classify equations and predict products? 4.5 and 4.6, which we're not to yet, is going to require everything you had to do for this, plus everything in chapter 4. So if this seemed like it harkened back to stuff we did a long time ago, it's because it did. And we still have more to incorporate before we move on to the second half of the course. We have one small item to cover before we leave section 4.2, and I asked you to have a look at it and even try some review questions on Google Classroom. So, remember that even though section 4.2 is about stuff you were introduced to in grade 10, namely reaction types, at virtually every type we add stuff, okay? So the thing we're adding to this last category is that there are 3 types of double replacement reactions. One of them you're already familiar with in grade 10, formation of precipitate. The second one is something we ended last class with, neutralization. Acid plus base gives salt plus water. Write the water as HOH, as if it was hydrogen hydroxide. It isn't, but because the OH comes from one reactant and the hydrogen comes from another, it makes it much easier to balance, okay? Now we're going to introduce the third type of double replacement, none of which you didn't see in grade 10. And this is where instead of getting 2 products like we expect with double replacement, we get 3 products. At first glance, it looks like it's hard to balance, but we're gonna treat it like double replacement and you'll see that it's actually pretty easy. So if you look at the bottom of page, I believe it's page 176. This will light up in a second. A few products of double replacement reactions are not very stable and spontaneously decompose to form water and a gas. The water and the gas is why there's 3 products instead of 2. So one of the 2 products turns into 2 things, all right? I think this is a mystery here. At first glance, the full equation of a neutralization reaction may not appear to represent double replacement. As 2 compounds form 3. Well, this isn't technically neutralization. Okay? We're not gonna write the products like that to balance them. We're gonna write the products as if it stayed straight double replacement, and then balance them like that. And then you'll see how it's real easy to turn it into this. The 2 categories are this: when an acid is added to a carbonate salt, or for that matter, a bicarbonate salt, one of the products is carbonic acid, which is this. Carbonic acid is very unstable. Unless it's kept under pressure, it immediately turns into water and CO2. But when we write products for this, we're gonna write that as a product and balance that. And as it turns out, however many of these we produce will be the same number of water and CO2. The other category is when we add a base to an ammonium salt. Because that product, which is also unstable, is ammonium hydroxide. That immediately turns into ammonia gas and water. But again, it makes as many ammonia and gas molecules as there are ammonium hydroxide. So we're gonna write that as a product and balance it for this type. We're gonna write that as a product and balance it for this type. And then however many carbonic acids we have, we're gonna convert them to the same number of water and CO2s. And however many ammonium hydroxide we have, we're gonna replace them with the same number of water and ammonia. So it's really easy, although if you wrote it like this, it wouldn't appear to be easy. So let me invent the couple. Sherry picks 2 real straightforward examples. Let me let's see. And I'm going to use 2 different colors so that you can easily see how we're treating it as double replacement. Somebody stores my felt pens. So let's start out new and then finish. Okay, let's try this. Let's do this one first. I wouldn't expect you to predict states unless I gave you the solubility table, but let's start off with this acid. What's that acid called? 8 ions make ic acids, right?
Hydrochloric.
So that's phosphor.
Clips.
And let's react that with, let's see. Something soluble, although it doesn't need to be soluble. Let's do sodium carbonate. Now, whether I pour this acid on solid sodium carbonate or a solution of sodium carbonate won't change the products at all. But as you guys may recall from the solubility table, sodium plus everything is soluble. So we're gonna write the product as straight double replacement. The sodium goes with the phosphate, the hydrogen goes with the carbonate. So we're gonna get sodium phosphate. Sodium is 1 plus, phosphate is 3 minus. So that happens to be soluble. And we're gonna get hydrogen carbonate. Hydrogen's 1 plus, carbonate's 2 minus. And we're not gonna put a state after this one because it doesn't stay as carbonic acid. We're just gonna balance it and then take it apart. So the least common multiple of 3 and 2 is 6, so 3 there and 2 there balances sodium. That gives me 2-phosphate, 6 hydrogens, 3 carbonate, 3 carbonate, so now it's balanced. But the 3 carbonic acid molecules turn into 3 waters and 3 carbon dioxide. And I'll try to stay consistent with the color. This makes 3 water. One of those oxygens is here, and that's liquid. And it makes 3 what's left, which is CO2 gas. So however many of these you have, you get that same number of water, liquid water and carbon dioxide gas. Now, don't leave it like this. You're replacing that with these. So do this in pencil, and then you don't have to use 2 different colors. But this is what you write as your formal answer, okay? But you don't write that before you balance it. You balance it first and then convert the carbonic acid to that. Make sense? Now that looks a lot harder to balance when you see it like that. But we didn't write it like that. We finished it. We turned the carbonic acid into that number of water and CO2. Now you can add states. Does that logic make sense? Okay, let's do one of these. Let's see. Actually, before I do that, let me show you that this also works with a bicarbonate salt. So it doesn't have to be carbonate, it could also be bicarbonate. You guys have all poured vinegar on baking soda, right? You see bubbles, right? Vinegar is this acid. It's a 5% solution of acetic acid. So most of it's water. So you're pouring that on baking soda. Solid baking soda, which is sodium hydrogen carbonate. So whether it's in solution or solid, you're still gonna see the same thing. You're gonna see carbon dioxide bubbles. So the sodium goes with the acetate, just like this sodium goes with that phosphate. So our product is gonna be sodium acetate. And that's actually sodium. And then the hydrogen, this hydrogen is gonna go with hydrogen carbon. Now this isn't the correct way to write the formula, but that H comes from acetic acid. That bicarbonate came from the sodium bicarbonate. And that's just H2CO3, right? So whether we pour an acid on a carbonate salt or a bicarbonate salt, we still get H2CO3. So that will, because it's balanced, we'll get 1 water and 1 CO2. Right? I mention this because the lab we're going to do at the end of chapter 4, I'm going to give you a handout, and on the handout there are 7 different lab stations, each of which is going to be a reaction type that you're going to observe and write the Gauss equation for. But I'm adding 1 more. And the extra one I'm adding is going to be an acid added to a carbonate salt in solution. And you'll see the bubbles, okay? What about a base added to an ammonium salt? Now let's do that one. Once again, we form a compound that's going to decompose into 2 things. So let's I'm going to pick a hydroxide compound that's soluble. I'll finish down the slow down. Break with tradition. Strontium. lithium hydroxide is actually soluble. And let's react that with an ammonium salt. And let's do phosphate again. Ammonium phosphate. Now, again, anything plus ammonium soluble, but I wouldn't expect you guys to know that. So we're gonna treat it as straight double replacement where the ions switch places again. The ammonium's gonna go with the hydroxide, the strontium's gonna go with the phosphate. So strontium is 2+, phosphate's 3-, so we need 3 strontium to 2 phosphate. Now that's actually not soluble, so that will give us a precipitate. And then the ammonium's gonna go with the hydroxide. Oh, pens are running out. There, that's right there. So ammonium hydroxide. And we're not gonna put a state after that, because it doesn't stay as ammonium hydroxide, but we're gonna balance it as straight double replacement. Start with the biggest compound and the polyatomic ion in the biggest compound, so I'd start with phosphate, 2 phosphate, 2 phosphate, 6 ammonium, 6 ammonium, 6 hydroxide, 6 hydroxide, 3 strontium, 3 strontium, so done. Now, it's balanced, except that that's not the product. This turns into the same number of ammonia gas and the same number of water. So one of these hydrogens stays with the OH. So we get 6HOH, and that's liquid. Okay. So however many of these you have, you get the same number of ammonia, gas, and water molecules. Don't leave it like this. Get rid of this and write that on the line. So the benefits of using pencil become instantly evident. So 6 ammonia gas up here. And just to stick with tradition, we'll stick with 6 waters. And you can leave it as H2O if you want, or you can write it as 6 waters. But again, had I written it like that and then tried to balance it, it would have been a little tricky. You get the idea? Yeah.
How do we know if it becomes a precipitate or like a solid?
I would have to give you a table, solubility table.
Okay.
Yeah, I put them in there because I know, but I can't expect you guys to know.
Okay.
Yeah. And technically, that's chapter 7, right? But if I expected you to determine solubility, I'd have to give you a solubility table. Same way you get an activity series, you won't have to remember that. Yep.
Why is the ammonium on the right side NH3 while
Why is the what?
the ammonia 3 like NH3 while the left side is NH4?
Because ammonium hydroxide is unstable. Anytime I make it, it turns into ammonia and water. Okay? It starts out as ammonium hydroxide. It just doesn't stay that way. Just like it starts out as carbonic acid, but doesn't stay that way. Okay? It's just balance it as straight 2 gives 2, and then take the compound out of the carbonic acid or the ammonium hydroxide apart. And then you know it's balanced, okay? Make sense? Yep.
Will we be expected to know if like a compound is unstable and we have to like break it
For
apart?
these 2 types of reactions, yes, you will. A base plus an ammonium salt, or an acid plus a carbonate salt, yeah. So let's look at the practice problems here. What type of reaction? Notice she says first classify them. Until you classify them, you can't predict products. So what type of reaction is this? This one? That's neutralization, isn't it? It is a category of double replacement, but acid plus base gives salt plus water. Write the water as HOH. In every neutralization reaction, balance it like that. So you're gonna get iron 3 chloride plus water. Now, I'm not gonna do them all for you, but because iron is obviously 3 plus, and then the H comes from the acid, the OH comes from the base. So pretend water's hydrogen hydroxide. 3 chloride, 3 fluoride, 3 hydrogen, 3 hydrogen, 3 hydroxide, 3 hydroxide, done. And you can leave it as HOH if you want. What type of reaction is number 2?
Single replacement.
Will it proceed? Where would you look to determine if this one will actually happen? What's the name of that table? Yeah, table of chemical reactivity, or sometimes just called the activity series. Is zinc above silver? Yes. The most valuable metals are near the bottom of the table because they're stable. And at the very bottom of the table is the most stable metal of all, gold. When we dig gold out of the ground, it's not in compounds, it's gold elemental form. That's why in the bottom of when you're panning for gold, you can see the nice gold dust in the bottom of the pan because it's not a compound. And when we dig a pharaoh's tomb up that's 5,000 or 6,000 years old, the gold is still nice and metallic and shiny because it doesn't react with anything. And that's why gold is at the very bottom. Silver's close, but not right at the bottom. What type of reaction is this? Ammonium salt plus a base. So that's going to produce cesium sulfide plus ammonia gas plus water. But balance it as straight double replacement. So the cesium's 1 plus, sulfide's 2 minus, that's one product, and the other product is ammonium hydroxide. So balance it like this, and then whatever coefficient you have in front of that, turn it into the same number of ammonia gas and water, okay? Now, this is also single replacement, but she hasn't put sulfide on the activity series for nonmetals. But halogens are way more reactive than sulfur's family, so that does proceed. So you're going to make lithium chloride and sulfur. Maybe it's a little unfair because elemental sulfur is S8, a solid, and that's maybe a bit of a stretch. Okay, that's the last set of practice problems in the section. You can look at the activity because it's not a bad problem solving one. But what I ask you to look at in the classroom is try a variety of some of the review questions. And notice how Sherry scaffolds her questions. She starts off with giving you the equations, reactants and products, and she wants you to balance them. Then classify them, and she does that down here. So that's really just section 4.1. Then down here, classify each. Look at B, which of the single replacement reactions would not proceed? We haven't started lunch yet, have we? Apparently some teachers have. So, that's a single replacement reaction, right? Will it proceed? So what's replacing what if this does proceed? Calcium's replacing hydrogen, right? Should it? Should calcium be able to replace hydrogen from water? It's above hydrogen, but it also has to be above what to replace hydrogen from water? Magnesium, and it is. So yeah, that'll proceed. Will that proceed? No. Gold replaces nothing from a compound. That's why everything replaces gold. Gold is at the very bottom. So no reaction here. Will that one replace? Will aluminum replace hydrogen from an acid? Look on your table. Isn't it above hydrogen? Not above magnesium. So it won't replace hydrogen from water, but it will replace hydrogen from an acid. Some of these, I wouldn't expect you to predict, but she doesn't ask you to predict either. She gives them to you. Now, this one here, scandium is not on your table, is it? Neither is rubidium. But rubidium's an alkali metal. And it is a very reactive alkali metal. So that definitely will proceed.
Good afternoon, staff and students. Let us prepare ourselves for grace before lunch. In the name of the Father, Son, and the Holy Spirit. Bless us, O Lord, and these your gifts, which we are about to receive from thy bounty through Christ our Lord. Amen. St. Thomas More, Blessed Edmund Rice, live Jesus in our hearts. In the name of the Father, the Son, and the Holy Spirit.
Notice
Amen.
that the next question, there's no products. So she's scaffolding that. You gotta classify them first, then predict the products, and then she doesn't give you any formulas. The last question, she just gives you the names of the reactants and continues on the next page. You gotta write the formulas for everything and then balance it. Okay? So I'm not suggesting you do all of them for Wednesday, but try a variety. And then I'll start Thursday's class with any issues with the 4-2 review, because you're gonna check your answers, and then we'll move right into 4-4. We're not doing 4-3. Okay?